All right, and our last talk of the session before the discussion is Vihang Mehta, who will talk about studying galaxy evolution with slitless spectroscopy with JWST, and looking forward to Roman as well.
All right. Okay, so hi, my name is Vihang, and I will basically be continuing where Kalina left off because we are, I'm also going to tell you more about passage results, but it will be widening the scope a little bit. Instead of just talking about mass metallicity relation, I will tell you about all the other cool things we do with passage to learn more about galaxy evolution. And so, as Kalina mentioned, there's a list of collaborators, and all the people that are highlighted in orange are here, and feel free to ask questions. My other goal, so with this talk, is also to drum up some excitement for the highlighted wide area survey and the Roman GRISM. I also work on the Roman GRISM pipeline, so I hope that by the end of this talk, everyone is just as excited about Roman GRISM spectroscopy as we are. A brief primer on what slitless spectroscopy sort of has been over the past decade. So it really sort of kicked off in high gear with the HST WIP-C3IR GRISM. Several surveys, including WISP and all the fruit surveys, as I call them, the figs, pears, grapes surveys, and glass and 3D HST were really the ones to sort of kick off the excitement for GRISM. JWST built on it with both NIRIS and NIRChem having GRISM spectroscopy capabilities, and there are several surveys that sort of use these instruments and these modes. As I mentioned, passage is the one that's going to be the focus here, but I in no way, shape, or form want to minimize any of the work that we've already heard from in this conference as well, from the other surveys. Euclid is on Sky and is now underway. We will hear lots more about Euclid, but what everyone's here for is Roman, which is, and I cannot stress this enough, very soon. Okay, I have a slide that's sort of covering similar things that you just saw in the previous talk. Passage, PI by Matt Malkin, who's here in the audience. We have 63 sort of individual fields. These are pure parallel, so we don't control where we point or how many filter changes and things we have. So there is some variety in what sort of filter coverages we get. Here's sort of the top right figure up here shows you the distribution of exposure times and the area that's the total area that's being covered. We reach up to about 383, slightly over 300 square arc minutes, 383 hours of observations. You saw a version of the 1D spectrum. I just wanted to highlight the 2D version of it. So here you can see the 2D spectrum for a nice galaxy with all the emission lines highlighted. You can also see some contamination that's been subtracted off from this other nearby object. So GRISM spectroscopy is a little bit challenging to work with, but I think we have it under control for the most part. And the line flux depths, so we basically, with JWST, as sensitive it is, the smallest amount of exposure time you can get is already going much deeper than what we would with Roman, but it has a much, much smaller area coverage. So the line sensitivity depths we get is reaching from anywhere from 10 to the minus 18 to 10 to the minus 17. You also saw this figure, this picture, but I just wanted to point out it again. So here is, I'll just blink between the two to get an idea of what slitless spectroscopy looks like. And you can obviously pick out emission lines, as Kalina had pointed out, but there's also a few other things to point out is you have different diffraction orders. So this is your initial first order. You get, zeroth order and higher orders that sort of muddy up your analysis a little bit. Passage in Cosmos. So there has been a lot of interest in Cosmos in cycle 1 for JWST, as expected. And so this has been the focus, and all of the results I will show you in this talk are mainly coming from fields in the Cosmos field. And the advantage here is obviously we have lots of photometry, ancillary photometry available for all of these objects to do things like comparison between photoz's and GRISM-Z's and things like this. So this is a compilation that has now been published. So if you are interested in using this, you can go to this paper. But just as a brief summary, you can see here's a spectroscopic redshift distribution that's shown in the plot up here. So we're basically covering objects between 1 through 3, and this is purely because we're sensitive to the strong optical emission lines, which are basically covered at these redshifts with the wavelength coverage that we have. Kalina showed a plot similar to this, but this is showing something slightly different. So one of the key things we want to do with prism spectroscopy is automate the fitting of redshifts. The idea here that we're showing is essentially on the x-axis is, in the y-axis is the automated fitted redshift. We're coming from a software called Grizzly, if you're familiar with that. But on the x-axis is the lots and lots of hours of work that our team put in for visually identifying redshifts or visually confirming redshifts. And even when we do this, there is still a lot of objects on off the 1-to-1, which on the order of about 35% overall and 12% even for multiple line emitters. So this is going to continue to be a problem, and we'll try to mitigate this as best as possible with all the tools that we have. So now I'm going to sort of run through some science results, and some of these are in progress, some of these are published, so bear with me, and I might go a little bit quicker through these given the amount of time I have. So first and foremost, we have star formation rate in galaxies. We have H-alpha, which is your gold standard for measuring the star formation rate. We can directly measure dust as well in galaxies due to the Balmer lines, and here is just plot showing the points from the galaxies from a single field, single passage field. So this is work in progress, but you can already see that we're filling out the parameter space much better than what was available before. Dust, as I mentioned, we can measure the nebular dust, and we can compare it with the stellar measurements for fields where we have photometry. So this is, again, ongoing work comparing the stellar dust that's measured from SED fitting compared to the nebular dust that we get from spectroscopy. Spatial result science. This is another very exciting aspect of prism spectroscopy, unique in some ways to spectroscopy, which is you get large samples of galaxies that you can basically spatially get a spatial map of the emission line. And here, given that we have the strong optical emission line, strong optical spectral lines, we can do metallicity measurements to get a metallicity gradient in galaxies. So that's what's being shown here. In the bottom, you have 8 galaxies that you have sort of azimuthally averaged metallicity measurements and plotted as a function of the distance from the center. And sorry, some of the text is cut off. I apologize for that. But the idea being we can measure this for the collection of galaxies, and this is a plot showing this gradient per kiloparsecs as a function of stellar mass. The points there, these galaxies are shown in these sort of yellowish points, gold points, and some expectations from simulations are shown as the curves. There's a lot of scatter. This is a difficult measurement to do, and we have very few galaxies, but this is something, again, Roman will help us with because we'll get more galaxies at comparable sensitivity depths. Protocluster science. I'm not going to spend time describing this. If you're interested in this, talk to Zara. She, I think, already gave a 90-second pop yesterday, but she has a poster on this. Please reach out to that. High redshift science. So the other cool aspect of slitless spectroscopy is you can do science at high redshifts, all the way up to redshift 8 and higher. The idea here is to essentially look for single line emitters that are Lyman alpha emitters, and you can use multiple different orientations of your grism to confirm the sort of reality of the line, or you can confirm that the line is real. And then similarly, you can also check for Lyman break in galaxies. Sorry. And so we have looked for we've searched for 7 photo Z selected sources in Cosmos, and we were able to confirm 1. The rest are too faint for our data to be able to do this. But this is, again, sorry, I did not mean to go forward. Something where Roman can help us with because it will cover a lot more area that you can get these rare objects with. I'm going to skip over this one in the interest of time. So where does this leave us with Roman? So idea with Roman is we have two dispersed elements on Roman, a grism and a prism, and I don't want to, again, minimize the science that we can do with prism, but the real excitement for the science that I'm describing here is to do with the grism element. So we're covering a very similar redshift range, or sorry, wavelength range, 1 to 2 micron roughly. We have a higher spectral resolution, and we have Hubble-like resolution, the spatial resolution. So we can basically do all of the science that I described here, but we can supercharge it. And here is a plot showing a simulated data. This is courtesy of the GRS PIT, and that's showing you sort of how the physical sort of data would look like for the grism and prism. And here's just showing you a single detector. Here's a figure showing all the detectors. So all of the data that I'm showing you pales in comparison with the amount of data that Roman is going to get. So this brings me to the highlighted wide area survey itself. So this is the survey that's going to use the grism element, and there are key advantages that I sort of highlighted here. Area, cannot stress this enough. The amount of area is very important. Competitive sensitivity, this is the other aspect. Roman is not as sensitive as JWST, but it is very comparable. And this is something you also saw earlier when Kalina was showing in her plot. You're basically limited to the high mass sort of range, but you're not, you're getting a lot more galaxies. So you can pin down the high mass end quite well, and you can do other analysis such as looking at scatter and descaling relations and things like this. Higher resolution is also important, and the complementary imaging as well, and I will describe some of this in the next slide. So again, the wavelength coverage being comparable, you can essentially do the science that I mentioned earlier, which is measuring these strong optical emission lines at cosmic noon. You can get their physical properties of galaxies, not just their ISM, but also their stellar populations, and you can do spatial resolved science. And the area really helps us. Something that's going to be unique to Roman is going to be probing at galaxy environments, because this is something that we haven't been able to do with the JWST thus far. And the other idea being you get statistically significant samples of galaxies, and these are unbiased samples. And this is the other key advantage of grism spectroscopy, because you're not pre-selecting any galaxies. You're just getting all galaxies in an unbiased sense. And combine all of this together, and you basically can, essentially do the science that I was describing earlier, but with much larger samples. The other for the high redshift science, Steve earlier had given a talk in this conference about cosmic variance and beating down cosmic variance with Roman, and so that's another aspect that's key for high redshift science. And that's not enough. So the simultaneous multi-band imaging, this is, it sounds trivial in some sense because it's imaging and you're getting spectroscopy already, but the key limitation for passage has been complementary imaging, because we can't get reliable SED modeling measurements and physical properties without this imaging. So I do want to stress the fact that getting imaging and spectroscopy both simultaneously on the same objects is very useful. Multiple roll angles help us disentangle overlapping spectra, and higher spectral resolution is also a key for identifying single line emitters such as the O3 and maybe in some cases the H alpha and N2 as well. I like to show this plot just for highlighting one thing. Obviously, we know the area that Roman is covering, but all of the results that I've shown you are like, maybe that dot that I'm pointing there is still too large. It is tiny compared to the area that Roman gets us. So lots of interesting science with JWST, and it's great, and it will continue to be great, but Roman is here, so I hope we are all prepared for the deluge of data we're going to get very soon. Thanks.
All right, thank you, Vihang. We can take one question. Okay.
Sorry, going back to the discrepant photo redshifts. I mean, for example, oh no, it's fine. It's more words. Is it possible to confuse, for example, lenses, right? So this is basically how some of the early clusters lensing surveys, they looked for, in Sloan, basically, redshift for a galaxy that's at low redshift with an emission line that was clearly a high redshift. So have you guys considered that? I mean, I don't think it's going to be 20% or even 12%, but it could, be a contaminant, which would actually be very useful for me.
Yes, that's absolutely correct. I think there are several people already thinking in this direction of using the GRISM spectra to identify lenses. I think you should be able to do it because you would essentially get two different sets of emission lines that are perfectly consistent with your original source if you cannot separate the lens, if it's small enough to not be separated in the spatial sense. So I think that is something that is being considered. I don't think any of the objects that are mismatched here are lenses because I think they're just line misidentifications because we've been, we've visually combed through the source's spectra to confirm that. But this is certainly a science application that I think people are already planning to do it, or it's certainly extremely possible and feasible to do that.
All right, let's thank Vihang once more and all of the speakers of the session.